Hey everyone, got a simple result for you today which I think has a fun and clever little proof. In today's Wrath of Math lesson, we'll be proving that for positive integers n and m, if m is greater than 1, then n is less than m to the power of n, strictly less than. That shouldn't seem too surprising. It seems pretty intuitive that raising a number to the power of n is going to be bigger than just that number n by itself. So let's go ahead and see how we prove it. How are we going to start making an inequality with n? One way we could go about it is by writing n as the sum of some simple terms that we could then replace with some bigger terms. Then we'd be able to have an inequality. That's what we're going to try. So we know that n is equal to 1 plus 1 plus 1 plus 1 plus 1 and so on n times, right? N terms of 1 being added together is clearly equal to n. So now we could replace all of these 1's with something greater than or equal to 1, and we'd be able to start making an inequality. What do we know is greater than or equal to 1? Well, certainly m, our number m, our positive integer m, to the power of k, where k is any integer and k is greater than or equal to 0, so k is a non-negative integer, m to the power of k is always going to be greater than or equal to 1. If k is equal to 0, then m to the k is going to be equal to 1, and if k is greater than 0, then m to the k is going to be greater than 1, since m is also greater than 1. So if we replace each one of these 1 terms with successively increasing powers of m, we're certainly going to have a number that's greater than or equal to this n, this 1 plus 1 plus 1 n times. So let's see exactly what I mean. We can replace each one with an increasing power of m. So we would start with m to the power of 0, then m to the power of 1, then m squared, and so on, all the way up to the nth power of m. Since we started at m to the power of 0, the nth power is m to the n minus 1, right? Because from 1 to n minus 1, that's n minus 1 terms, and then throw in that extra 0 term, that m to the power of 0 term, that's n total terms. So we've replaced each one of these 1's with a number that's greater than or equal to 1. So we know we have this less than or equal to relationship. We could have a strict inequality, but since n is allowed to be equal to 1, we could end up just having 1 equals m to the power of 0, and so we need to have that less than or equal to, not just strictly less than, because again, n can be equal to 1, which is where the equality would pop up. Okay, now perhaps you recognize this. Again, this is the sum of the first n powers of m. And what is that equal to? Well, we proved this in a recent lesson. The sum of the first n powers of a number, any real number other than 1, starting at m to the power of 0, this is equal to m to the next power, so m to the n, minus 1 divided by m minus 1. I've got a video proving this result by induction and a video on a more clever proof that doesn't use induction. So if you're not familiar with this result and its proof, go check out those lessons. I'll leave links in the description. We're going to proceed taking this result for granted because we have proven it. Again, this is the sum of the first n powers of m starting at m to the power of 0, and this is what it's equal to. So we can do some substitution here. This, by this result, because m is a positive integer greater than 1, so it fits into this equality just fine, this is equal to m to the power of n minus 1 divided by m minus 1. Clearly, if m was equal to 1, we'd have a problem there, dividing by 0, but m is not, so we're good to go with this substitution. Now we can continue an inequality. Since Since m to the n minus 1 is getting divided by m minus 1, we might say, okay, well clearly this is less than m to the n minus 1, but we can't quite use the strict inequality because it's possible that m is 2, in which case the denominator is 1, and so this would actually be equal to this. So we need to have less than or equal to. And again, that's because m to the n minus 1 is getting divided by some positive number that has to be greater than or equal to 1. So this is certainly less than or equal to the numerator, m to the n minus 1. But now we can finally get into strict inequality territory, because m to the n minus 1 is certainly, indubitably, without a doubt, without a second of question, it is less than m to the power of n, right? Take 1 away from m to the n, obviously you would have something that is a lesser number. And look at that. Oh man, it's choking. Our whole string here, it starts with n. N is less. N is less than m to the power of n. Look at that. Because n equals this, which is less than or equal to this, which is equal to this, which is less than or equal to that, which is less than that. N is less than m to the power of n for positive integers n and m, where m is greater than 1. It's a corollary of this result, that the sum of the first n powers of any real number, which is really cool that this works for any real number. We're just dealing with integers here, but this works for any real number other than 1. The sum of the first n powers of that real number is the real number to the next power, minus 1, divided by the number minus 1. Really cool. And so with this result that we've just proven, n is less than m to the power of n, plus the power of this beautiful result here, very shortly we'll prove one of my favorite theorems, the basis representation theorem. I hope you'll look forward to that. I hope this video helped you understand this result and its proof. Let me know in the comments if you have any questions, need anything clarified, or have any other video requests. Thank you very much for watching. I'll see you next time, and be sure to subscribe for the swankiest math lessons on the internet. And a big thanks to Valo, who, upon my request, kindly gave me permission to use his music in my math lessons. Link to his music in the description.